All right, good morning. It's 10 o'clock. Time to start. We'll go ahead and take attendance again today. Antonio's here. We want to make sure he gets credit for it. All right. And then also, I gave everybody one of these little slips of paper. I did not give everyone these slips of paper. All right. So this just is a reminder of when the review sessions are, when the exams are, and where the exams are. So we will be taking, those of you that are registered for this section, will be taking it on Tuesday, 9:45 in the morning. And it'll be in 11:04, which is where the review sessions have been held previously. Okay? All right, and then the other thing that is coming up is next Thursday, next Thursday's the ACS exam. I'm hoping to have scores posted by Friday morning. And then there'll be review sessions on Friday afternoon and then Sunday also. Okay? All right. Let's go ahead and move forward. So a couple other things just to point out. Tomorrow I'm out all day. There's a quiz on Canvas that's due before noon on Friday. End of semester evaluations you've been invited to participate in. If you do 3 of them, you get an extra credit point added to your exams. Right, and then the other thing that I don't have up there, there's going to be a quiz on the last day, and it's a quiz that you can't use your cheat sheet on, I'll give more information as it comes up, but based on performance, you can get extra credit applied to either of the exams, all right, and I think it's 2 points or something, so, okay, all right, but I'll talk more about that either later this week or next week. All right, things that we've talked about previously. So we've covered the Clausius-Clapeyron equation. You explored a little bit in the homework that's due on Friday. From there, we talked about the Gibbs energy and its relationship to chemical potential. And we derived this expression that's sort of important. The Gibbs energy is equal to the chemical potential times the number of moles, right? And from this equation, we've generalized it and said that this, for any molar quantity, right? And we looked at an example looking at molar volumes. We can say that the thermodynamic quantity that we expect to observe is the partial molar quantity for each of the components in the mixture times the number of moles. From there, we introduced the Gibbs-Duhem equation. We've derived it. Basically, the bottom line is that there's a direct relationship between the chemical potentials of the components of a mixture. And in fact, the other thing is that they're not generally equal to each other. Right? We also showed that the chemical potential for a component in the solution is the same in all the phases that are present at equilibrium. And we derived a relationship that we're going to be using, if not today, on Friday. The chemical potential for each component in our mixture is the same in the liquid or vapor phase if it's at equilibrium. That's given by the chemical potential when it's pure plus RT ln, and then the pressure of that component over its pressure when it's pure. All right. We've introduced the idea of an ideal solution. Basically, we said Raoult's law is followed over all its compositions. All right. Okay, and then the questions that we're going to ask today, how are the compositions of the vapor and the liquid related in the coexistence region? Up to this point, we've just been talking about the pressure due to the liquid composition. We're going to see that we also will get the gas phase composition of the mixture. There's going to be a relationship between the pressure and the boiling point. So let's just remind ourselves, we have boiling occurring whenever the external pressure equals the vapor pressure of our solution. All right, that's what we've covered before, right? And the other thing I guess I want to say at the outset here, if I have a high vapor pressure, does that correspond to a low boiling point or a high boiling point? If I have a high vapor pressure, that means it's easy to evaporate, right? So is it going to be easier to boil it or harder to boil it? It's going to be easier, all right? So I just want to write that. So high P vapor corresponds to low boiling point. or a lower vaporization temperature. All right, we'll get to that in a little bit. So we're going to talk about the impact of composition on boiling points. This will lead to a discussion of distillation. From there, we're going to talk about delta G of mixing for an ideal solution. We might not get there today, but we are going to try to talk about non-ideal solutions today. All right. So things that we've covered before, just want to make sure that we reiterate these. So when we use this asterisk, that means that we're talking about the pure substance. We've been talking about the mole fraction in the liquid phase. That's given by X sub I. That's one of the components, number of moles of that component over the total number of moles. What we're going to do today is talk about the mole fraction in the gas phase. All right. So it's still going to be the number of moles of the component that we're interested in over the total number of moles. But we also can talk about this in terms of the pressures, right? And so this is the same as the pressure of component I over the total pressure above the solution, right? That's pretty important, okay? All right, the other thing I want to do is just define the term volatile. So volatile refers to how easy it is for something to vaporize. So ease of vaporization. So how many people use cologne or perfume or something like that, right? Those tend to be highly volatile, right? Otherwise you wouldn't smell them. Does that make sense? Right. So if I have an easily evaporated substance, that basically means that it has a higher equilibrium vapor pressure. Does that make sense? Right? And what we've just established is if I have a high vapor pressure, I have a low boiling point. If I have a low vapor pressure, I have a high boiling point. Okay? All right, so the last time that we met, we just finished discussing Raoult's law with respect to one component. I want to finish off one thing here. We have previously shown that the chemical potential of our component is given by the chemical potential when it's pure RT plus RT ln, the vapor pressure of that component, over that vapor pressure whenever it's pure, right? So this works for all gases, right? Or for all solutions. Right? If we impose ideal behavior, then what we can say is that the chemical potential of our component is given by the chemical potential when it's pure plus RT ln. And now when we look at Raoult's law, we recognize that Pi over Pi star is the same as the mole fraction. Right? So I can put in Xi, right? And again, this is for ideal solutions. Okay? Make sense? All right, and so last time that we met, we looked at this Raoult's law for one of our components. We can see that's a linear relationship, all right? Now what I want to do is introduce a second component, all right? So my second component, I'm going to put the X, the mole fraction on the upper axis. So on the left side, whenever I only have component 2, that means it's mole fraction. When this one's 0, this one's going to be, what's the mole fraction going to add to? 1, right? So that's going to be 1. And whenever I'm completely component 1, the mole fraction of component 2 is 0. Does that make sense? Okay? All right, so that also says that when I have no component 2, I have no pressure due to that component, right? And when I'm 100% component 2, that pressure is going to correspond to the pure component 2. So that's P2 star, all right? And then I can draw in a line that represents Raoult's law for the second component. Make sense? All right. And then the other thing to recognize is that now my total pressure in this over this solution is going to be due to the sum of the two partial pressures, right? And that comes out to be a linear relationship that connects the two endpoints, right? So let's take a moment to talk about what this line equation is going to be. All right? So P total will be our y, all right? And then x1 is our x-axis, right? And I need to know what my slope is, right? All right, so to get the slope, I'm going to draw a line across here, right? This line is delta x, right? And if I go across the whole thing, what's delta x equal to? It's equal to 1, right? And then delta y is going to be equal to the difference between the vapor pressure of one of my components when it's pure and the vapor pressure of the other component when it's pure. Does that make sense? All right. So it should be P2, or P1 star, sorry, P1 star minus P2 star. And then our y-intercept will be P2 star. Does that make sense? Okay. Now, we didn't really explain that this is going to be linear. So this is a derivation that I've lifted out of the textbook that I want to talk through. Now, the thing that's a little weird about what the textbook did was that they are looking at P total as a function of x2. Right? So they're really looking at that total pressure as a function of this second component's composition. Right? We could do the same derivation for component 1. So P total is going to be P1 plus P2. It's an ideal solution, so P1 is x1 P1 star, P2 is x2 P2 star, and then we know there's a relationship between x1 and x2. x1 is equal to 1 minus x2. So that means I plug that in for this. I've got x2 here, x2 here. I can collect the terms, right? And so that's what's done down below. That gives me my y-intercept as P1 star and my slope as P2 star minus P1 star. Right? But this demonstrates that it's linear. Okay? Make sense? Okay, so let's do a quick calculation. So we have a 1-propanol, 2-propanol solution that is ideal. If x1 propanol is 0.4, what's x2 propanol equal to? 0.6. All right? And then I can ask the question, what's the total pressure? And in order to get there, I need to know what the partial pressures are. All right? So I'm going to start with P1 propanol. P1, right? It's going to be x1 P1 star. All right? In this case, that's going to come out to be 0.4 times 20.9 torr. And that comes out to be, I can't calculate that in my head, 8.4 torr. All right, I do the same thing for 2-propanol, P2. That's going to be 0.60, the mole fraction, times its vapor pressure when it's pure, 45.2 torr. And that sums to 27.1 torr. All right? And then we know that the total pressure will be P1 plus P2, and that gets me 35.5 torr. Does that make sense? Okay? All right, so let's take a moment to graph that. So down below, I'm going to put x2 propanol on the lower axis, so it's going from 0 to 1. And on the upper axis, we'll have x1, which means it's going from 1 to 0. All right? So when I have none of my 2-propanol present, the only thing I have present is 1-propanol. All right? So that says on this side, the left side, I'm going to have a pressure of 20.9 torr. All right? And on the right side, when I'm 100% 2-propanol, then I'm going to have 45.2 torr. Okay? And because it's an ideal solution, I have a straight line that connects the two. All right? And this line is going to be the relationship between the total pressure and the mole fraction in the liquid phase. All right? So I'm just going to put xi there. All right? The point that we've just calculated is for 0.4 or 0.6 for 2-propanol. All right? So that's around 0.5. We're going to call that 0.6. I come up there. That intersects at a total pressure of 35.5 torr. Does that make sense? Okay? All right. So the other thing that we recognize is that whenever this has reached equilibrium, I now have a solution in the gas phase above it. All right? And what I want to do next is ask what's the composition of the gas phase. All right? So we'll start with Y1. So this is Y1 propanol. That's going to be equal to number of moles of component 1 over the total number of moles. And what we said at the outset of lecture today, right, is that this is going to be the same as the partial pressure for component 1, and this will be the total pressure for the solution. Right? And so in that case, this is going to come out to be 8.4 torr over 35.5 torr. And that turns out to be equal to 0.24. Okay? All right, so one thing that we can do before we go forward here is we step back and we say, well, clearly my composition of the gas phase is different than the liquid phase. Right? And that's fundamentally because I have a different vapor pressure contribution from my two components. Okay? And I can calculate the same thing for 2-propanol, Y2. That's going to be 27.1 torr over the total pressure, 35.5 torr. And that comes out to be equal to 0.76. Okay? All right, so that also says that at this total pressure of 35.5, this is the mole fraction of the liquid, but now I have another mole fraction that I can plot on the same graph. All right? And so 0.76 is around there. I come up there, that's at the same pressure. This is going to be for the vapor phase composition. Okay? Does that make sense? All right? All right, before we go forward, let me just stop and ask a question. 1-propanol, 2-propanol. Who's more volatile? 1 or 2-propanol? The 2-propanol, it's got a higher vapor pressure. It's easier for it to evaporate. All right? So more volatile. All right? And what we see is that our 2-propanol composition in the vapor phase is increased over that of the liquid phase. Does that make sense? All right? It should make sense, right? Because it's easier to evaporate. Right? Now I could calculate that at this liquid fraction, I would get something to the right for the vapor phase. Right? So what I know is that I've got this endpoint and this endpoint where they have to coalesce. And then in between, I can draw through a smooth curve there that represents the liquid or the vapor composition. And this upper linear trace is the liquid composition. Okay? All right? And as long as I'm between these 2 points, I have a differential in composition between my 2 phases. And I'm always enhanced with respect to the more volatile component. Does that all make sense? Okay? All right, and that's what's said here. The more volatile component is enriched in the vapor phase. All right. So this is the same graph, just done a little bit more neatly than what I was able to do. And what we're going to do is just talk through it a little bit and try to get some relationships. So we're going to start here with this pressure and with an overall composition. Because I'm clearly above the coexistence region, I know that at that point, I only have one phase. I'm in the liquid phase, all right? Liquid only. And X2, that is the mole fraction of the liquid phase, is the same as XA, our overall composition. Okay? All right. And then what I'm going to do is I'm going to just start to lower the pressure. All right? So when I get to point A, right there, that is the first emergence of the vapor phase of this solution. Okay? So we can say vapor forms. And at that point, X2 is still XA, which is 0.8. All right? But at that pressure, my vapor phase is going to be around 0.9. Does that make sense? Okay. Okay, and just to broaden the thing, we know that if y2 is 0.9, y1 is 0.1, right? And if x2 is 0.8, x1 is 0.2. Right? Because of the relationship between the mole fractions, right? All along the path from A to B, we have coexistence of the liquid and the vapor. All right? So this really says that along this path, I've got a liquid solution and I have a gas phase solution. And it's enriched with the more volatile component. All right? By the time I get to point B, that represents the pressure at which I have my last little bit of liquid. It's about to go away. All right? So last liquid. And X2 at that point is around 0.62, and Y2 is around 0.8. All right? Now, if I reduce the pressure further, then I'm completely in the vapor phase. Right? And then the composition is going to be the same as the initial overall composition. Okay? All right. Along point C, there is a little line drawn across here. All right? That's called the tie line. And that relates the mole fractions. And we will see the number of moles in the liquid phase and the number of moles in the vapor phase. Right? So we're going to be doing a derivation shortly that shows that we can get the information about what's in the liquid phase, what's in the vapor phase. Okay? All right, so in this derivation, we're going to be talking about component 2. We could be doing the same thing for component 1. This is just arbitrarily selected. All right? So the one thing that we can say is that the mole fraction of component 2 in the liquid phase is always going to be equal to the number of moles of 2 in the liquid phase over the total number of moles in the liquid phase, right? So when I don't have a subscript, that means it's the total, right? And again, that's just being consistent with the textbook, right? And then I can say that for my gas phase, the composition is given by the number of moles in the vapor phase of component 2 over the total number of moles in the vapor phase, right? We're going to label this with an A. Okay? All right. And a little foreshadowing here. So if I'm interested in knowing the number of moles of component 2 in the liquid phase, I'm going to just multiply both sides of this by the total number of moles. Right? And if I want to know the number of moles in the vapor phase, I'm going to multiply the mole fraction in the vapor phase of component 2 times the total number of moles in the vapor phase. Right? So the other thing that we can do is we can think about this composition in terms of overall composition. So XA, all right? And that's going to be equal to, because we're talking about component 2, that's going to be equal to the number of moles of component 2 in the liquid phase and number of moles in the vapor phase. So N2 liquid plus N2 vapor. And I need to divide that by the total number of moles, which is N in the liquid phase plus N in the vapor phase. All right? We're going to label that B. Okay? We good? All right. And our goal from this point on is to come up with an expression for number of moles in one phase over the other. I don't remember which one we're going to have in the numerator. Number of moles liquid phase over number of moles in the vapor phase. All right? That's what we're going for. Okay? All right, so I'm not going to read through the next text. We're just going to talk through the verbiage, or we're going to go through the derivation itself. The basic idea is that we know that the number of moles of component 2 is the same no matter which way I look at it. Okay? All right, so the moles of component 2 is going to be the same as moles of component 1. So using equation B, that's down here, right? If I want to know the number of moles of component 2, well, that's going to be moles in the liquid and the vapor phase. So I take XA times the total number of moles, right? And if I want to know the number of moles of component 2 from the equation A, right, that's going to be the mole fraction of the vapor phase times the total number of moles in the vapor phase, and the mole fraction of the liquid phase times the total number of moles in the liquid phase, right? So this comes from, this side comes from equation A. This side comes from equation B, all right? And then we do some algebra, all right? So I just multiply through XA times the number of moles. That gives me this. Do the same thing for the right, well, the right side doesn't change, all right? And at this point, what I'm going to do, because I'm looking for moles in liquid phase versus moles in vapor phase, I need to collect those terms, all right? So that means I need to subtract Y2 and vape from both sides. That's what's done here, or is that how I did it? Well, at any rate, I collect the terms. So I get these on the same side, and I get these on the same side. Okay? Make sense? All right. And then what to get where I want to go, all I need to do is factor out N vape times Y2 minus XA is equal to number of moles in the liquid phase times XA, overall composition, minus the composition of the liquid phase, right? And from there, I can easily get to N liquid over N vapor, right? So N liquid over N vapor is equal to Y2 minus XA divided by XA minus X2, all right? Okay, so, and then we just step back and look and see if this is consistent with how we've interpreted this graph. If Y2 is the same as XA, right? If those are the same, then we're talking about point B, right? And if those are equal to each other, then this comes out to equal to 0. And that says I have nothing in the liquid phase, okay? So this is referring to point B, all right? And then if I flip it over, I'm not going to write it, if I flip it over, if my overall composition is the same as that of the liquid composition, then I'm at point A, and then I don't have anything in the vapor phase. Okay? And between those two limits, this gives me the ratio of moles in the liquid phase versus the vapor phase. We good? Okay? All right, so we didn't expressly state this at any point, but these vapor pressures only have meaning if I'm holding the temperature constant. All right, so at constant temperature, this gives me the relationship between my liquid and vapor phase and the composition. All right. Now what I want to do is transform this into a vapor phase, a temperature phase diagram. All right. So down below, we're going to take that same information, and now we'll still have x2 and y2 on our lower axis, so that's going to be going from 0 to 1. And the upper axis is going to correspond to x1 and y1, and there we'll be going from 0 to 1 in that way. All right? And now what we're going to choose to do is hold pressure constant and look at temperature. All right? So this axis will be temperature of vaporization, which means if the external pressure is the same, we're going to have boiling. All right? So that also gives us the boiling points. Right? Right? And we're not going to do a rigorous derivation here. We're just going to use qualitative information. Right? So if I look at the information up above, I see that my pressure of component 2 is greater when it's pure than my pressure of component 1 when it's pure. All right? So that tells me that which component is more volatile. It's going to be 2, right? And if it's more volatile, how's that going to translate into its boiling point? Is component 2 going to have a lower or higher boiling point than component 1? It's going to be lower, all right? So I'm going to put here T2 star, right? That's going to be the boiling point of pure component 2, all right? Now on this axis, I'm going to put the boiling point of pure component 1. All right? And we expect that between these two temperatures that we're going to have a mole fraction for a liquid phase that's different than the mole fraction for the vapor phase. Right? And so I'm just going to draw in two curves that connect these two. Right? This is where we're not doing it quantitatively, but we're doing a qualitative thing. Okay? All right? And the next thing that we need to do is we need to determine which one of these corresponds to the liquid composition curve and which corresponds to the vapor composition curve. So if I come over here and I say that's the boiling point of our solution, all right, that means that this is going to be one of the components, this is going to be the other composition, all right? Okay, and the way that we can reason out which curve is which is to, again, say, well, who's more volatile? Component 2. So we expect to see an enrichment in component 2 in the vapor phase over the liquid phase. So putting that together, which curve, upper or lower, corresponds to the vapor phase? It's going to be the upper. So this corresponds to vapor composition. Right? And so that means that this is Y2. Right? And this lower curve references the liquid composition. And that says that this is X2. All right? Does that make sense? Okay, so let's take this one step further. All right, so we're going to take the same information and we're going to flip the axes. All right, so this was X2, Y2 to propanol. Now we've got 1 propanol, which means up above is the 2 propanol. So we basically have just flipped it. All right, so this is X2, Y2. All right. Okay, so same information, just using a different x-axis. All right. Let's say I start at point A, all right, and I let it equilibrate. This is the liquid composition. This is the vapor composition. What I could do is I could go in and take that vapor off. So I remove this, all right? I remove that fraction, and then I condense it and I let it equilibrate again, right? And that gets me over here, right? And then I can collect that vapor off, and I can again condense it and let it equilibrate. And what am I doing to that portion that I keep pulling off and letting it equilibrate? It's becoming more pure, all right? And it's more pure with respect to the more volatile component, right? And in fact, this is what distillation is. Right? Now, if you think about this experiment that I've talked about, you don't want to keep pulling off your vapor, condensing it, because you're wasting a lot of material, right? I'm throwing away the liquid phase every step of the way. So what's done is it's transferred into this column, and this whole this column has this temperature through this temperature occurring, and you have repeated equilibrations and condensation and vaporization throughout this column. All right, this is the hot portion of it. All right, so this is where the heat's added. So this is at high temperature. Right, this is at low temperature. All right, and in here you've got condensation and vaporization. Right. So those of you that are chemical engineers, have you talked about petroleum separation? Right? There's a temperature gradient in here, which means that each level you can pull off a different fraction of your petroleum product. Right? Those of you in organic chemistry laboratory, you've done distillations, I assume? Did you monitor the temperature? So when you monitor the temperature, what you find is that this temperature is going to be the same as your more volatile component's boiling point. Right? It's sitting at that point. So that means you're getting pure low volatile or high volatile component. Right? So pure, and this is the high volatile or high vapor pressure, more volatile. Okay? Does that make sense? Right? And when this component's gone, if you've done these mixtures before, what happens to this temperature that you're reading? It goes up, because now you're starting to get the other components that are higher boiling point. Right? Make sense? Okay, so we're going to skip over this section for now. We might come back there later today. All right. So everything that we've talked about up to this point has been about ideal solutions. Right? Now we're going to talk about deviations from ideal. Right? So what we're going to basically point out is that most solutions are in fact not ideal. Okay? All right. Now we haven't talked about this before, but when we have ideal solutions, what we're saying is that the interactions between liquid 1 and liquid 2 are identical. So liquid 1 and liquid 2 molecules in that solution are the same as liquid 1, and liquid 2, liquid 2. Right? So we see deviations whenever we have non-equal interactions between them. So caused by unequal interactions liquid 1 with liquid 1, liquid 1 with liquid 2, and liquid 2 with liquid 2. Okay? And if you think about the interactions, if you're bringing two different substances together, there's really two possibilities. They can either have stronger attractive interactions, or they're going to have disruptive interactions, right? Those are the only possibilities, right? Okay, and then those of you that took Gen Chem, and they may say this in organic, like dissolves like, right? And that's referring to polarity, right? So we see that played out here. So here I've got on the left side CS2. That's a linear molecule, analog to CO2. I can't say analog to CO2, right? It's linear. It's nonpolar. This is polar, all right? So we would expect that they're going to be disruptive, of each other whenever they get mixed together. Over here, I've got trichloromethane and acetone. These are both polar molecules. That is leading to an increased attractive interaction. Okay? All right, so when we look at the composition curves, when we have dissimilar polarities, we see that rather than following Raoult's law, we see that our vapor pressure is higher. And that should make sense, right? When I bring the two components together, we're disrupting the intermolecular forces, and therefore it's easier to get them into the vapor phase. Does that make sense? All right. And then whenever I have stronger attractive interactions, I see, rather than following Raoult's law, I see a decrease in the overall pressure, okay, of each of the components. Okay, so positive deviations occur from Raoult's law due to disruptive liquid 1, liquid 2 interactions. I don't like to say repulsive, because if they're repulsive, then we don't expect them to be in the liquid phase at all, right? Then they'll go into the gas phase. So they're just weaker interactions, all right? And then the negative deviations, that means that wants to be in the liquid solution more. That says by combining these two compounds, I have more stronger attractive interactions. All right, well, let's look at our graph a little bit further and say, well, you know, we like Raoult's law. Does it hold ever? All right, so this is Raoult's law, Raoult's law, Raoult's law for each of the components. Do we see a behavior of our components that are following Raoult's law anywhere? That looks pretty good, right? That looks pretty good. That looks pretty good. And that looks pretty good. We agree? All right? So what these all have in common is that these are when they're for the component that's in the majority. What do we call the component of a mixture that's in the majority? All right, multiple choice. Solvent, solute. If it's in the majority, it's the solvent. All right? So when X1 is the solvent, as its composition approaches 1, we're following real ideal behavior. Ideal behavior for component 2 when it's the solvent in the limit of mole fraction 1, similarly over here. All right? So for our non-ideal real solutions, whoops, I need to change back to a pen. P, whoops, as Xi solvent approaches 1. Okay? So it works for the solvent as X of the solvent approaches 1. Okay? Make sense? All right. So when we look at the other extreme, we see significant deviation from ideal behavior. But one of the things that we can recognize is that I can draw a tangent in there, and a tangent in there, and a tangent in there, and a tangent in there. And when I do that, that says in this little region, I have linear relationship for the solute between the mole fraction and some constant. Does that make sense? Similarly here and here. We good? Does anybody know whose law holds at that point? That's Henry's law. All right? So as our solute composition approaches 0, the pressure, or the partial pressure, is approaching Xi times a constant. All right? And what we can say is that the pressure of the solute is equal to the mole fraction of the solute times a constant that is associated with that component. And that constant is called the Henry's law constant. All right? Does that all make sense? So we can describe the behavior for our non-ideal solution for the solvent in the limit as its pressure or as its composition approaches 1, and we can describe it for the solute as its composition approaches 0. Okay? All right, so let's look at an example. So this shows the vapor pressure above a water alcohol solution. All right? Straight line is Raoult's law, and we have 3 different alcohols on here. All right? So the one thing that we see is that in every case for the alcohol, as its composition approaches 1, we have Raoult's law being obeyed. All right? And we can reason through which one of these curves corresponds to which alcohol. So water is a polar or a nonpolar solvent. It's polar, and it's superpolar, right? So we'll just say very polar, right? Because it's got lots of opportunities for hydrogen bonding, right? So now I have these alcohols. I have methanol, ethanol, propanol. Which one of those is going to be least polar? It's going to be the propanol, right? Because I have a large nonpolar group attached to the hydroxide. So that's least polar. And by the same reasoning, methanol will be the most polar. All right? So we think about interactions between the particles, water and methanol, water and propanol. Which one is going to be least disruptive? It's going to be the methanol, right? And so that tells us this curve is methanol's curve. And the one that deviates the greatest is going to be 1-propanol. Okay? All right. And then we ask the question, well, how can I use this graph to determine what the Henry's law constant is? All right? So when we think about Henry's law constant, what we're saying is we're talking about the solute in the limit as its pressure, as its mole fraction approaches 0. So that's down here. All right? So if I want to know what Henry's law constant is, I draw in a tangent, and the slope of that tangent is going to be the same as Henry's law constant for, in this case, it's going to be propanol. And if I want the Henry's law constant for methanol, I'm going to look at the slope of this curve, right? KH methanol. And all we're saying is in this region, we can describe this linearly. Okay? Does that make sense? All right, I think that's where we're going to leave it for today. I let you out 2 minutes early. Whoa, 1 minute early.